Okay, so the talk is Angels, Demons and Antimatter, the science behind Angels and Demons, which is it is Dan Brown's sort of second bestseller. I think there's 8 million copies been sold. And the main science behind it is this question of antimatter. And so the plot, if you haven't read it, basically, in a nutshell, it's about a crazy anti-religious sect that goes to the world's biggest laboratory just outside Geneva in Switzerland, and they steal a canister of antimatter. They take it off to Vatican City in a helicopter, and they're planning to blow up the whole country. And so our hero is this Harvard historian who gets called over to investigate this mystery. And he meets a particle physicist, and they race around the Vatican, actually. And they try and find the antimatter, and they want to get it back to CERN before the bomb explodes and the Pope dies. So that is the plot in a nutshell. How much of this is actually fact or fiction? Good place to start is at the beginning, where our hero gets a phone call from this guy. He says, "My name is Maximilian Kohler. I'm a discrete particle physicist." I'm not quite sure what a discrete particle physicist is, whether he means he's good at keeping secrets. But this is our introduction to the science in the book. So what actually is particle physics? Well, it is the study of the mind-bogglingly small fundamental particles of matter that make up our universe, and also combined in that, how they interact with each other and the world around us. So just to get a kind of a thought on this, in terms of getting your head around the scale, what is mind-bogglingly small? How small are we talking about? If we look at this, the smallest thing I could imagine that we can sort of see is a human hair. And so this is a human hair which has been looked at under the microscope. And so the width of this hair is 0.06 millimeters. And it's got this logo printed on by the University of Birmingham, which is pretty amazing. So if we take that as our starting point, and then if we think, we're going to zoom into this hair to just one carbon atom. So that thing that you see there ringed is just one single carbon atom, and the image there is an array of carbon in a structure. And that takes us down to 0.2 nanometers. So we've zoomed in enormously now. This is kind of naught and with a decimal point, then another 8 zeros after it. So we're talking tiny scales, just getting down to one atom. Particle physics goes further than that. Here's the atom, just looking at it. Inside, we've got the nucleus, which is the protons and the neutrons, and orbiting that are the electrons, which is kind of the familiar picture of the atom. That's not to scale, of course. The electrons will be much further away than that if we were to draw it up to scale. Particle physics then looks, we go into the nucleus, so we're looking at the protons and neutrons. And this is 1 femtometer. So that's, particle physicists describe that as 10 to the minus 15. So that's decimal point and 14 noughts after it. So it's incredibly small. So we think we've gone really tiny, but actually particle physics is looking inside the nucleus. So we take the nucleus, and then we find that inside the proton and the neutron are even more particles. And these are actually the fundamental particles of matter, and they're called quarks. So you can see in the proton, it's got 2, U stands for up, 2 up quarks and 1 down quark. And the neutron has got 2 down quarks and 1 up quark. And at the moment, we think that quarks are indivisible particles of matter. Now, we thought that about the atom a little while ago, so who knows, we may find that we can split the quarks as well. But at the moment, that's as far as we've got. So here are quarks, just to kind of set the context. There's 6 of them that we know about. There's the up and the down. There's 2 called the charm and the strange. They've got wonderful names. Particle physicists obviously like to keep themselves entertained by coming up with funny names for these things. And then there's the top and the bottom. And the top is actually the huge green circle that you see there, because one of the mysteries in particle physics is that the top has got this enormous mass compared to the others. And that's something that they're looking into at the moment to try and find out why that's the case. So particle physicists have got this model called the Standard Model, which is essentially their equivalent of the chemist's periodic table of elements. And it includes the fundamental particles of matter that we know about so far, which is a pretty amazing achievement to have got this far and been able to work it out. So we've got the quarks that we've just met. There's 6 of those. And then there's another group of particles called leptons, they're also fundamental particles. We know one of them, that's the electron. There's a heavier version of the electron called the muon, and another heavier version of that called the tau. And then there's also these strange particles called electron neutrinos, muon neutrinos, and tau neutrinos. And they basically, they come from cosmic rays in outer space. So in a second, while I'm talking to you, 1 billion of those will have shot through your body. They're very strange particles, which also particle physicists are trying to find out about. So we've got this wonderful model of what the universe is made of. And it divides up into these 3 families, the different colours, which is something that they're not quite sure why that's the case, but it's there and it's something they've observed. And these particles here are basically the particles which make up the everyday matter that we see around us. So the up and the down quarks form the protons and neutrons in the nucleus. The electrons whiz around those to make the atoms. And then the electron neutrinos are the neutrinos that might be flying through us most often. And so it's pretty incredible that absolutely everything in the world around us, whatever you're looking at, is made up of really just 3 particles, the down quark, the up quark, and the electron. So that's really kind of summary of where particle physics is at today. So this is what Dan Brown's talking about when he starts off the book about this world of particle physics. This is what it's all about. And just quickly, I talked about the fact that it's about these particles. It's also about the way they interact with the world around us. And so there are a few more particles to introduce, which are the particles which they carry the forces, if you like. So the first ones are the W and Z, and they carry something called the weak force, which affects all the particles in the standard model. And this is the force which basically it determines how atoms decay. So for example, without the weak force, the sun wouldn't go through its kind of radioactive decay and it wouldn't shine and we wouldn't have light on Earth. So it's life on Earth. So it's a really important force. The electromagnetic force is probably the force that we're all familiar with. The photon is a packet of light. It carries the electromagnetic force. And that affects just these top 9 particles. And the other one is the strong force, which is got this wonderful particle called the gluon, which literally glues together the quarks inside the nucleus. Otherwise, everything would fly apart and we basically wouldn't be here. But there's one more force which is missing from the standard model, which is a big problem for particle physics at the moment. And that force is, of course, gravity. And we think that there might be a particle called the graviton, which conveys gravity around the universe, but we don't know yet because no one's found it. So that's another big mystery that people are looking out for. So that's kind of particle physics in a nutshell, very briefly. What are particle physicists really like? In the book, I think he's the director of CERN, this Maximilian Kohler, is this mysterious gentleman in a wheelchair described here. Notice a man in a wheelchair exiting the building. He wore a white lab coat. No, scientists don't wear white lab coats anymore in physics labs, certainly not in CERN. These are the guys that run CERN, well, they may not look entirely normal, but they are perfectly normal people going about their daily business. Maximilian Kohler does not exist, but as you can see, there's a Maximilian Metzger there who is in charge of things at CERN. So it may be that Dan Brown has done his research and got some inspiration from that. So what is this place CERN that he describes in the book? He says that it's a place where passports are unnecessary. The particle physicists have a standing arrangement with the Swiss government. Sounds extraordinary. What sort of place do you have government access to go in and out of? Well, unfortunately, this isn't entirely true. This is CERN. You can see the Alps in the background. It's based on the French-Swiss border, so there is passport control on site, but unfortunately, scientists don't have free will to come and go as they please. So that's not entirely true. He describes the place as a sort of mix between an Ivy League campus and this ultra-modern campus where there's rectangular ultra-modern structures of glass and steel. Well, that's partially true. The top picture on there is a building at CERN called the Globe, which is actually a sort of museum display type building. It's not really where the experiments happen. And the one below is where an experiment happens. It's an experiment called Atlas, which is, this is the big control center there. So he's kind of right. He's got the atmosphere right about this place. But really, what's interesting about CERN is what they do there. And he quite rightly states their interests lie within the atom's nucleus. So what's it really about? It stands for the European Organisation for Nuclear Research. That's absolutely true, what he says in the book. And it means nuclear, not in the sense of nuclear power and weapons, but nuclear in the sense of literally looking inside the nucleus, which is what they meant when they started this up in, I think it was 1951. He says it's the world's largest scientific research facility. That's absolutely true. It's the biggest laboratory experiment collaboration in the world. It's an amazing place. There's physicists from 20 member states around Europe, and they all gather there to pursue this kind of this avenue of finding out what matter is made of. Founded in 1954, the laboratory was one of Europe's first joint ventures. I think after the Second World War, it was before Europe kind of agreed to join the European Union. They agreed to join CERN. So it was a pretty amazing sort of collaborative effect that they had there. There's more than 6,500 physicists that work there, so it's an enormous place. They represent hundreds of universities and nationalities. But it's not just huge in the number of people, it's actually an enormous site. This again is an aerial shot of CERN. You can see the Alps again in the background. The kind of white strip, 2/3 of the way up, is in fact Geneva Airport. And this ring is 27 kilometers round, and it represents the particle accelerator, which is a tunnel underneath the ground. And at the various points which are ringed on the circles on this ring are points where they've put detectors to do the experiments. So it's a massive place. You sort of literally have to drive across it when you're working there. So it's quite extraordinary. But what's exciting is the stuff that's underground. And again, Dan Brown's absolutely right. The mainstay of the experiments are underneath the ground, 100 meters underground. And this is an artist's impression done on computer graphics of what the particle accelerator tunnel looks like. And this is in fact what the accelerator will look like in 2007, and it's an accelerator called the LHC, which is mentioned in the book. If my little clicker will work, there we go. So quite rightly, Robert Langdon, our historian, says, what does LHC stand for? Trying not to sound nervous, because at this point he's been taken underground. It's all a little bit mysterious. LHC actually stands for the Large Hadron Collider, which won't be familiar to most people. Hadron simply means, it's the name for a group of particles. One of those particles which can be described as a hadron is the proton, which we met earlier. And basically what happens, this is a real-time picture of the LHC, which is being built at the moment. What happens is that two proton beams will get whizzed round the accelerator, and then they smash into each other. And when you get a collision, you get new science and new particles happening, and so people can find out what's going on. So that's basically what the LHC was all about. So again, Dan Brown is absolutely right. It seems like a massive venture. Robert Langdon says, you're telling me that CERN dug out millions of tons of Earth just to smash tiny particles? Well, yes, actually. But it's the forefront of, it's cutting-edge technology what they're doing there. When they switch this accelerator on in 2007, it will produce the highest ever energies created in a laboratory on Earth. And what it's actually going to do is recreate the conditions just billionths of a second after the Big Bang. It's amazing to think that we can actually find out what was going on at the beginning of the universe by sort of cranking up these particle accelerators. So Dan Brown hasn't overblown that at all. That's absolutely right, however extraordinary it may seem. So just to whiz through, some of these slides I'll sort of pass over for time-wise, but just so you get an idea of what high energy means. Particle energies are measured in these things called electron volts, which you don't have to worry about too much, but if you know that the definition of this is that 1 electron volt is the amount of energy that if you accelerate an electron through a field of 1 volt, that's the amount of energy it gains. So if you think about the fact that your house mains kind of draw 240 volts, then you start to think about that, and two protons that collide in this accelerator will have an energy of 14 tera electron volts, which is massive. So you can sort of see the sort of energies we're talking about in comparison. However, it sounds big. Dan Brown starts blowing this up, and you think, wow, this energy sounds a little bit worrying. This is all going on underground in Geneva. But to put it in context, 1 tera electron volt, however enormous that seems, is actually roughly the energy of a mosquito landing on your nose. That's all it is. However, think about a proton. It's 1 billion times smaller than a mosquito. So when you then kind of multiply that up and you think, you know, what does the proton feel as it kind of smashes against the next one in the accelerator? Well, it's kind of, when you do the math, it's at full power, the beams of protons that collide will be about as energetic as a car traveling at around 2,100 kilometers an hour. And the energy that's stored in the magnetic fields will be bigger than that because they've got enormous magnets down in there to bend the particles round. And that's equivalent to a car traveling at about 10,000 kilometers an hour. So it's a pretty major collision that you get in there. So it talks in the book about these magnets in the tube kind of pushing the particles around. And it says that the accelerated particles circle at over 180,000 miles per second. Now that seems amazing. It's almost true, not quite. 180,000 miles per second is actually the speed of light, which is, if you're sort of working in meters, then that's 3 times 10 to the 8 meters per second. And actually the speed of light is the universal speed limit. Nothing can go faster than the speed of light. So Dan Brown's not actually quite right. They can't be going faster than that at the accelerator. But they are going very, very close to it. What actually happens in the LHC is that one proton going round the 27-kilometer ring will go round over 11,000 times a second. It's going that fast. So they've got pretty amazing equipment to kind of keep up with that. And the beam of protons that go around, they can exist whizzing around this accelerator for up to 10 hours at a time. So in that time, they can cover about 10 billion kilometers, which is the same distance to going out to Neptune and coming back again. So it's extraordinary scales that we're talking about. But he's right when he says that magnets are used to push the particles around. You can see a picture of them here. These blue things in the tunnels are actually series of magnets going all the way around the 27-kilometer ring. And so what they use, they're super-cooled magnets to control the beams at such high energies. They use just over 1,000 of these superconducting magnets. So why do they use magnets? Well, charged particles are affected by magnetic fields. So these charged particles that are whizzing round, you can actually move them and send them where you want to if you've got a big magnetic field there. So that's how they actually get to bend them round in this ring. They use superconducting magnets because in a superconducting material, if you get it at very low temperatures, then it allows electricity to flow through it without any resistance. So it's a far more efficient way of pumping lots of energy in and electricity. So if you've got more electric current going through, you've got a higher magnetic field, and so the more you can bend the particles around and accelerate them. They operate at minus 270 degrees Celsius, something that, again, Dan Brown picks up on in the book. Absolutely true. It's only 3 degrees above absolute zero, which is the coldest temperature you can have in the universe. So it's basically the world's biggest fridge, this kind of 27-kilometer fridge underground. And the magnets, they operate at 4 Tesla, which basically means, when you work that out, it's 100,000 times the Earth's magnetic field. So they're the strongest magnets in the world, well, beyond the world, that they've got operating down there. So everything's really at cutting edge. This is a picture taken just last month, actually. There's an engineer in the accelerator tunnel, and he's installing one of these magnets here. So you can see there's all the pipes coming off. That's for all the cooling systems. And the beam pipe, where the particles actually zoom along, is that one in the middle there. And the casing is all these superconducting magnets around it. So that's actually what's going on down there at the moment. So Dan Brown's description of these kind of polished chrome tubes is all very futuristic, but pretty much accurate. And this is just to show you how the particles actually whiz round. Just see if I can get the mouse pointer to come up. Lawrence, are you able to do that from up there? Thank you. So there's actually these feeder rings. Before it goes into the big ring, they kind of get the speed up by whizzing them around these first rings. So you put one bunch of protons, actually there's billions of protons in a bunch, and they send another one in, and they start to go around the main ring in opposite directions, and they get them up close to the speed of light, and then they collide at a very precisely determined point in a detector, which is where the science is done. So this, you're seeing the two, we're looking end on now, as if the particles are coming and crashing in the middle of this picture here. And all the stuff around there is the detector, and you get to see these particle tracks come out, and you find out exactly what's happened in the collision, and you see all the new particles that have been created. And I think Dan Brown, he's done his research quite well, actually. He even describes these pictures that are up on the wall of these particle events. So they're pretty impressive things. He describes that while he's down there, this historian, Robert Langdon, they say, without warning, inside the accelerator tube, particles of matter began appearing out of nowhere. Well, it wouldn't be without warning. They wouldn't have built all this if they didn't know that was what was going to happen. And certainly particles of matter don't appear out of nowhere. You can't create matter out of nothing. It's created out of the enormous energy of the collision. And so this, again, is just another of those pictures. And you can see all these coloured tracks in the middle are tracks of where the particles have shot out from the middle of the collision. And by looking at how the tracks bend and where they finish, you can work out what sort of particles you've got there. And in one of these collisions, you're always creating, to keep the balance of energy and matter, you can't just create things out of nothing. It creates a very nice kind of symmetrical situation where you get a particle of matter and you also get antimatter created at the same time. So that's happening quite routinely in these collisions. And so when Vittorio Vetra, our particle physicist in the book, announces grandly, "Director, you're looking at the world's first specimens of antimatter," it's not strictly true. The world's first specimens of antimatter were actually created way back in 1932 in California. This guy, Carl Anderson. And this is a bubble chamber, which is the old-fashioned way of detecting particles. And you can see coming in on this picture, there's two curved tracks going like this, which I hadn't observed before, and they were pretty much symmetrical. And that's actually an electron coming in, and its antimatter equivalent, the positron, which is the opposite charge of the electron. And that was the first time it was ever viewed. So it's not true that the first one was created at CERN. So what is antimatter, this mysterious substance which he's based the whole book on? Well, basically every fundamental particle that you've got has got a sort of identical counterpart, which is exactly the same apart from its charge. So if you've got a negatively charged electron, its antimatter equivalent is the positron, which is positively charged. And the same if you had, for example, an up quark, which has got this charge of plus 2/3, because there are 3 quarks within a proton, so the charges on quarks come in thirds. Its antimatter equivalent is simply minus 2/3, and it's the anti-up. So you've got these kind of mirror particles in nature. And what's amazing about that, you could meet quite feasibly your antimatter equivalent, but you wouldn't know it. There would be no way of telling until you decided to shake hands with your antimatter equivalent, at which point you would both annihilate. So you'd never know any more about it, which is a bit of a shame. But it's absolutely possible. Now, there's the word annihilation in the book. Robert Langdon says he doesn't like the sound of that. It's a pretty amazing event. With antimatter, when it comes into contact with normal matter, there's this massive energy explosion, and 100% of the mass of these two particles or these two objects is converted instantly into energy. And it's the only totally efficient conversion into energy that we know of in nature. And it's all down to Einstein's famous equation, E equals mc squared, where E is energy, m is for mass, and you simply times that by the speed of light squared to work out how much energy you get out of just a massive object, out of anything. And there's a big mystery behind antimatter, which is that we actually owe our existence to a sort of an asymmetry between antimatter and matter. When the Big Bang occurred, matter and antimatter must have been created in equal quantities. But if there was lots of antimatter still hanging around, we'd be annihilating with it all the time, and the world couldn't exist, the universe couldn't exist. So it must be that at the beginning of time, antimatter disappeared for some reason, and we don't know why. It must be due to a tiny little difference that we're not sure about, other than just the difference in electric charge. So the universe is entirely matter, or it could actually be entirely antimatter. We don't know, because it's the only one that exists. We just know there's an anti-something out there. So all of this mystery around antimatter, which Dan Brown sort of uses in the book, is again, absolutely valid. Now, when we start to get on to this idea of an antimatter bomb and antimatter being transported from Geneva over to the Vatican, it starts to get a little bit fuzzy. He says that they have antimatter traps where the antimatter is suspended between intersecting magnetic fields. Again, it's kind of true. In 1995, CERN actually assembled the first anti-atoms, and it was anti-hydrogen. So normal hydrogen is just one proton in the middle and an electron orbiting around it. It's very simple. And so anti-hydrogen is exactly the opposite. It's an anti-proton in the middle and a positron, which is your anti-electron orbiting around the outside. And they actually put these together. This is where they did it. It looks very messy. And you can see the sort of accelerator tube there, and the yellow thing up the top is where they stored the antimatter. But the anti-hydrogen atoms are actually made in flight. They were traveling at the speed of light. So they couldn't really sort of stop them and make a measurement and find out what it was all about. So certainly they didn't have these canisters hanging around. However, today CERN uses a new thing called the antimatter decelerator, which literally slows down the antimatter they make so they can have a better look at it. Now, the physicist in the book says, "My father built a reverse polarity vacuum to pull the antimatter positrons out of the accelerator before they could decay." total Star Trek guff. It's absolute nonsense. I have no idea what that means. It doesn't exist. It's just, I think, Dan Brown trying to come up with some scientific jargon to impress. What they do, the antiproton decelerator is a much smaller ring at CERN. They've got a vacuum pipe to pump all the air out of it, because if the antimatter was coming into contact with air, then it would annihilate, so they have to do it in a vacuum. Magnets, again, to bend it round and control them. And all these radio frequency cavities and electronic circuits are literally to slow the particles down so they can get a good look at them. And this is one of the experiments called Athena, which is a real-life antimatter experiment. They do exist. This is where they made some of these anti-hydrogen atoms. And this is the antimatter trap. It's not a canister that you can take away and put in your pocket and use to blow up somewhere, at the moment anyway. This is a huge room, and they have to pump all these cooling systems and electricity and all the rest of it in to keep this antimatter trap for millionths of a second. So that's really the reality of it. This is the latest experiment. There's an antimatter trap down the side there, which consists of all these complicated gold electrodes and things to keep it trapped. So in short, it's not very portable. Dan Brown has stretched the fact a little bit there. Now, the main issue with this is this idea of 1/4 of a gram of antimatter, which is what the physicist in the book says she's made. And the scare about this, of course, is that much antimatter, she says, could annihilate everything in a half-mile radius. Well, we can kind of work that out. And I won't do too much maths. This is just a little bit, just so you can see, really, because this is something that people have got quite worried about. People are creating antimatter all the time. You know, could this really be a destructive force that we've got in the world? Well, does 1/4 of a gram of antimatter, which is what they have in the book, actually convert to what they say it does? In the book, she says it converts to 5 kilotons, which is the equivalent of 5,000 tons of TNT. And just for reference, the Hiroshima bomb was about 20,000 tons of TNT. So she's talking about a fairly major force here. Well, energy is measured in joules, which is just the unit it's measured in. You don't need to worry about that too much. And what we do know is that 1 kiloton of TNT corresponds to 4 times 10 to the 12 joules. So this enormous amount of energy. That's 1 kiloton of TNT. So we know that much. Now, going back to Einstein's equation with the equivalence of mass and energy, where you can swap them around, we literally plug it into the equation. We say, well, the amount of energy will equal the mass, which is 1/4 of a gram of antimatter, multiplied by the speed of light squared. You literally plug that in, and you find out that the energy of 1/4 of a gram of antimatter equals 22,500 terajoules. So that's 10 to the 12, so with all those noughts going after it. So it sounds vast. And we can work that back out. So we say, we know how much a kiloton of TNT is in joules. So compare that to the amount of energy that 1/4 of a gram of antimatter is. And we find that actually it's about right. 1/4 of a gram of antimatter is equal to 5 kilotons of TNT. Dan Brown has obviously done some maths in a previous life. So that's absolutely right. So we can remain worried about antimatter at this stage. But it gets worse. For the antimatter bomb, the bit that he forgot, we're actually talking about 1/4 of a gram of antimatter annihilating with another 1/4 of a gram of matter. So we're actually talking about 1/2 a gram of explosion. And that's 10,000 kilotons. So we're now talking about half the Hiroshima bomb. So Dan Brown's actually underplayed it a little bit in terms of the amount of energy that might be released here. So he says antimatter was the ultimate terrorist weapon. It had no metallic parts to trip detectors, no fuse to deactivate. It does sound like a terrifying force. Well, that's definitely not true. Firstly, the canister traps, the only way to catch antimatter is to have these intersecting magnetic fields which kind of hold it in place in the center in a vacuum. That's all going to involve metal. Of course, that's going to trip detectors to start with. We've seen that they're not portable anyway. They're housed in vast rooms. And more crucially, we're never actually going to make enough antimatter for a bomb. 1/4 of a gram doesn't sound very much, but when you have a look at it, CERN makes around 100 million antiprotons a second. Now that sounds an awful lot. You think, well, we could probably make a bomb out of that. There are 6 times 10 to the 23, so again, with all those noughts after it, antiprotons in a single gram of antihydrogen. So we do need quite a lot just to make 1 gram. So we can, again, do a bit of maths, and we work out that we'd actually only need well, not only need, we would need 6 times 10 to the 16 seconds, so that's 15 noughts going after it, to make a single gram of antimatter. Now, we're only talking in seconds at the moment, but when you work that out, in terms of number of seconds in a year, you actually find that you would need 2,000 million years to make 1 gram of antimatter. So Dan Brown's talking about all this happening now. Firstly, the LHC, which he talks about, is not up for operation until 2007. So it'll be a little while until they've amassed enough antimatter to make a bomb. Also, I should point out that the LHC doesn't actually make antimatter itself. That's just to look at the protons going around and look for new physics. It's a kind of the separate antimatter facility at CERN, specifically for looking at that. So that's also not quite accurate in the book. So we're feeling a bit more comfortable now. It's going to take a very long time to create all this antimatter. I think it's very unlikely that we will see the Vatican going up in the antimatter equivalent of an atomic bomb sometime soon. In fact, when you work it out, the amount of antimatter that CERN has produced, if you add it all up since they started creating matter, in fact, I think it's adding it up over the last 10, 20 years or so, it would actually not blow up the Vatican. Will it blow up the world? Will it blow up the universe? No, it will light a single light bulb. That's the amount that's actually sitting around cumulatively. And when they do make it, they make such a tiny amount, it flips in and out of reality just in millionths of a second. So they really don't have that facility at the moment to make that kind of quantity of antimatter. So unfortunately, Dan Brown's climax in the book is highly unlikely, although very worthy of a good story, I have to say. If you haven't read it, then you should do. It's a very exciting read. So given that that's the kind of fact and the fiction about what actually happens with antimatter, what is the reality of what we use it for today? Well, the place where you might come across it is if you go for a PET scan in hospital. PET stands for positron emission tomography. Now, we've met the positron. It's the antimatter equivalent of the electron. What happens is when you go for a PET scan, they inject you with a radioisotope, and positrons are given off when these radioisotopes decay. And you actually get annihilation happening. In this case, they're looking at the brain. So the positrons collide with electrons in your matter and annihilate. They give off gamma rays, and you can detect these, and you can image the brain. So there's actually a real sort of use for antimatter beyond destructive weapons and the world of fiction. Of course, the Starship Enterprise is obviously powered by an antimatter drive, which, again, is not possible now because when you've seen the sort of scale of CERN and how it operates, they actually have to, they can't operate in the winter months because they draw so much electricity from the surrounding grid that Geneva would kind of power down as a city so they could keep whizzing the protons round. So it's a very, although antimatter annihilation is a 100% conversion from mass to energy, it's actually very inefficient because the amount of stuff you have to put in to create the antimatter in the first place is way beyond the energy that you get out. So at this stage, I'm afraid it's very unlikely that we'll be able to power ourselves into outer space using antimatter. But you never know, it could happen in the future, and hopefully Dan Brown will write a book about that one as well. So that's really the end of my talk on antimatter. I hope you found that interesting if you have or haven't read the book. And if you've got any questions, please feel free to ask me.
Thank you very much, Anna. Does anybody have a question for Anna to start us off?
Hi.
Was said that that's the largest one currently being built. Is anybody planning to build a larger? Or?
The accelerator. Yeah, I've sort of given the wrong impression that CERN in Geneva is the only place that does particle physics and has accelerators. There's another accelerator in Hamburg, in Germany. There's a couple in the United States. And the next big plan, which is their planning stage at the moment, they have to look so far ahead, it's incredible. It's called the International Linear Collider, which will be the next step up from the energies even in this accelerator. And that's going to be, because you can, this is obviously a circular accelerator, you can also have linear accelerators, which they've also got in the States. And they've decided that that's the way they want to go. They want to use linear acceleration. I think they're going to have it supercooled again. They had the choice between supercooling all the equipment or using it hot, as they call it, warm. So yeah, the next plan is the International Linear Collider, which is not just going to be a European venture, but because of the scale of it, because of the amount of money that has to go into it, has got to be a global venture, which is, there's very interesting talks at the moment between factions, because everybody wants it in their country, because it's a very prestigious thing to have. So yeah, but that's a long time down the line. I mean, that would be kind of, I don't know, actually, maybe sort of 20, 30 years before they sort of start talking about really putting that in place. But yeah, the quest for more energy is ever going on. So we will see more things to come after the LHC, certainly.
Is it fair to assume that Lord Lucan must have met the antimatter equivalent?
Well, this is one explanation. Yeah, it could very well have happened. So
at the same time as Elvis and Shergar.
yeah, it's the explanation for everyone, but they've all vanished, so we're not going to see them in a past life. No, I mean, it really is true. What I love about this is that it sounds so fictional and so extraordinary, but there really could be sort of antimatter beings in another universe somewhere or something. It's really true. People do create antimatter all the time, albeit in tiny quantities, and it's an extraordinary property of antimatter and matter that this annihilation happens when we do come together, and it's not fully understood, which is why people are pouring all this effort into particle physics to find out, because it does explain where we come from, why everything is the way it is, and I think that's quite an exciting thing to be finding out, really.
It's a little worrying with that PET scanning, though. I always knew it involved positrons, but I didn't realise actually made inside your brain.
Annihilating in your head.
Yeah,
it's true, but then it's on such a tiny scale. I mean, nothing's going to be destroyed in the brain really when you're talking about that, and cells regenerate all the time, so it's not a problem. But yeah, I mean, a lot of people when they first hear that think, wow, I don't think they tell you that in hospital. Yeah, it does. Good question. Absolutely. Well, there are varying theories for dark matter, and it's an interesting field now where particle physics and cosmology are actually overlapping with each other. They are looking to answer the same questions. So there's this idea that dark matter is accounting for most of the matter out there in the universe. I've put forward a very positive picture here that particle physicists seem to know everything about dark matter. Well, actually, we only know about 5% of all the matter that must be out there, or that we know must have been created at the Big Bang. So certainly, in the LHC, what they're hoping is that at higher energies, they will find more particles that they haven't actually sort of maybe not even accounted for in their standard model theory, and might be particles that can account for this dark matter. They've got some wonderful names, which you probably know. They're WIMPs, weakly interacting massive particles that they think might account for dark matter, and MACHOs, which are these massive equivalents. So yeah, no one knows actually. What's exciting about this experiment is that certainly that Atlas experiment, which I showed you, they're putting in all this energy into it, and they don't actually know what's going to come out. So it may be that they find out more about that in this experiment. And certainly, they've put forward lots of different theories about. I think neutrinos for a time were thought to be, possibly dark matter, and that's all sort of gone by the by because they thought they were massless, and now they found they've got a tiny mass, and it wouldn't really account for the amount that's supposed to be out there. So the answer is not there yet, but it could be after 2007. You have to check back in.
Any further comments for Anna? Well, in that case, thank you very much for a fascinating talk.
Thank you. Thank you for
Before
coming.
we all